Welcome to ilectureonline, and here we're going to talk about vapor pressure and partial pressure as it applies to the amount of pressure that the water vapor can have in the atmosphere. So going back to this graph that we've seen before, here it depicts the pressure of the vapor that will be a result of the temperature. For example, at 0 degrees centigrade, vapor pressure can only be 0.006 atmospheres, which is a little bit over 4 millimeters of mercury. And as the temperature increases, the vapor pressure can increase. So whenever water is at a higher and higher temperature, the rate of evaporation will increase. And if you put that into an enclosed container, the vapor pressure will build up to that maximum pressure that can exist at that level, because at that temperature I should say, because at that point we'll reach a dynamic equilibrium where the rate of evaporation will equalize the rate of condensation, and so that will be the pressure that will then be maintained for the water vapor above the water. But what happens when this water container is exposed to the atmosphere? Because there's atmospheric pressure there's lots of gas, nitrogen gas, oxygen gas. What happens to the water vapor when it evaporates? Well, it actually begins to displace the molecules in the air molecules, and it becomes part of the atmosphere. And it turns out the amount of the water molecules that can exist in a vapor phase in the atmosphere depends on the atmosphere's temperature. So it turns out that the amount of vapor pressure, the partial pressure of the total atmospheric pressure, is equal to the vapor pressure that would exist if you were to place a container in an enclosed environment and allow it to evaporate until dynamic equilibrium is obtained. So that vapor pressure